Here we are, guys. I'm Artin. This is going to be about pretty much like modern transformer stuff, because transformers are like the backbone of a lot of things. So let's just get into it. So yeah, we're going to talk about brief history of like large language models up to this point, transformers and attention. Ew. Then we're going to talk about the cool stuff like quantization, ways to like compress your model, even run it on your laptop, and then ways to train your model faster. One of them is like called LoRA, and then we'll get to some cool like attention kind of stuff like I'm alluding to, and maybe some like thing called selective state space models.
Wait, you're not sharing your screen right now.
Not.
Yes.
Oh. Oh, there. Yeah, that makes sense. Is that good?
Yeah.
Oh wait, what? How do I? Okay, that works.
Yeah.
Sure. And then okay, can I?
Click the left.
This?
Yeah.
Okay, there we go. That looks good. Okay, sure.
You're covering up the logo then.
Oh, I am. Oh, I'm sorry. I'm sorry. I think that's just gonna be a sacrifice. Okay, we're good. Okay, yeah, we're gonna try to speed run these first two because this is kind of like we need to know how transformers work to explain the advancement in transformers. But we're gonna try doing that here. Again, this is like I've done this a lot. So this is yeah, wait, let me go back. We're gonna actually live split this. So let's go live split. We're gonna oh, there it is. It's already here. Okay, yeah. We got intro segment, step one, tokenization. We're gonna do positional, we're gonna do mask extension, we're gonna do feed forward, we're gonna explain softmax, and then we're gonna answer questions. And we're gonna see how long this takes. So intro segment, we're running.
Wait, you want to full screen the tab so you don't show your bottom like the
I don't. What do you mean? How do I?
the chaos.
Oh, yeah.
Yeah,
Ignore
there
that.
we go.
Oh, that's what you mean. Okay.
Yeah.
So yeah. So intro 2017, we got transformers from Google. This is attention is all you need. This has like an insane amount of citations, if you can see. It pretty much allowed for training in parallel, and it fixed certain like limited memory of RNNs, and allowed for like long range dependencies. That's like the general gist. Transformers originally was meant like kind of a sequence to sequence model. It takes in a sequence like a sentence in some language and it can output it in another language. But today we actually sometimes just use an encoder or decoder for a lot of different tasks. BERT is one of them. BERT was, yeah, it's an encoder. BERT is pretty much just the encoder. Yeah. It does what you expect it to do, encodes, so you can use it to like classify text as spam, not spam. It's the same way as like you classify an image, you compress it down to representation, and then you can extract features from it. In this case, we did spam, not spam, but you could also say, is it a positive sentence? Is it a negative? Are they happy about it? Sad about it? Whatever, right?
But what's a transformer?
What's a transformer? Is that the next slide? I don't think so. No, that question's gonna be a little, you gotta wait a little bit for that one. Yeah. So yeah, let's just skip that. BERT was deployed. This is the history, then we're gonna get to actually the architecture. So then BERT is again a part of the transformer architecture. It was deployed in 2019 actually, and this improved search a lot. If you actually use Google search in like after and before October, you might actually notice it where it can better understand what you're saying. So like, let's say you said, can you get medicine for someone pharmacy? It would just give you like random prescription medicine because it said pharmacy and medicine. That's probably what you want. But after, because BERT was really good at understanding language and again, transformer architecture, it understood you wanted to have like a friend or family pick up prescription for you, right? Which allows search and speed way better. So again, transformers were used and I mean, yeah, popular. Great. Okay, this is the big one that everyone cares about. I think this is GPTs and OpenAI. So GPT, ChatGPT stands for Generative Pre-trained Transformer. It's now, instead of the encoder, we're just focusing on the decoder part of the transformer. And the idea is you're just predicting the next word. Yeah, we're keeping kind of high level for now. Okay, there's a little comparison. Encoder, you can encode it, extract stuff. Decoder, you can generate stuff. Great. So yeah, GPT-3 came out June 2020 now in our timeline. And it was, yeah, it was insanely massive in parameters. This took what is it? I have it next. Yeah. They $4 million to train and like 570 gigabytes of like have you ever like written a text file? Like I can't even get to like kilobyte, but like gigabytes of text, right? Which is just like that's insane. It's an insane amount of text. And by the way, oh yeah, that's filtered. Sorry, that's filtered from 45 terabytes of just internet. So it's kind of actually insane to think about how much text that is. Like transformers are very what people call like data hungry. They need like an insane amount of data. But if we have that, they're actually best performing. So continuing, yeah, GPT-3, this was its breakdown. It was like the internet, it got like 3% of it was Wikipedia. There were books in there. Yeah, data set breakdown. A lot, actually Reddit. Reddit was like a large portion. So that's interesting. So yeah, results. Yeah, I just copied some slides from before. When GPT first came out, people were like, what? This is crazy. And I saw this Twitter post and I was like, oh my gosh, you can like ask it to like write a thing and it writes the HTML code for a button, and we were like freaking out. Now we're like, okay, ChatGPT, do my entire CS homework assignment. Why can't you do it? You're so bad, But like at the time, we're like, it can code. We're getting replaced. It's going crazy, right? And then I love this one. I had a high school AP Gov assignment, and then I had it autofill it. That was really nice. What it's really good at doing is following pattern, right? So they gave me 2 examples of 1 year, and then it's like a president, and then like a little, like summary of them, and then and then they gave me another example of the next year and the next president. So then it knows just like again, like pattern following, just keep repeating that over and over, explaining the next president and that kind of stuff. That's where it really was good at, that's where, yeah. Anyways, it kind of failed in that kind of idea of it just following a pattern of what is most likely isn't best for us when we want to talk to it. So this was actually the base GPT-3 model. If you typed in the playground, like explain the moon landing to a 6-year-old, it would most likely, like a lot of times, it would just repeat, like this is the output. It would say explaining whatever, 6-year-old, explain whatever. Because again, it was just trained on the internet to predict the next token, right? And on the internet, if it has a question, it might be a test bank or a question bank, and it'll just keep listing more questions because this is like the most likely. But for us, we don't want just this. We want like an answer. So what you have to do back in the day was you just prompt it and you say, okay, like you give it maybe a few examples, right? So yeah, again, another one. If you ask it to explain code, it would not explain the code. It would then give you an A, B, C, or D, which is like what? But like if you think about it, on the internet, if you saw some code in a question, the most likely thing following it was probably like a test, and then what would follow is like an A, B, C, or D answering of it, right? So it kind of makes sense, but yeah, so it's not very good at following instructions directly. But what we saw though was that at 0, these are called shots, they call them, which are pretty much just examples. So if you give it no examples, just ask it, hey, explain the moon landing. This is how well it does. But what they saw is if you give it 10 to the 0, which is just one example. So you show, okay, explain, like cars, and like cars work by like wheels or something, I don't know. And then you ask, explain the moon landing, it will have insanely greater performance, right? So it's only one example the model really needs to be able to actually know what you want it to do. And again, if you do like 10 examples, it's going to be better. But the whole point was that it just wasn't good at following the thing off the first go, right? So yeah, these are examples of shots. So again, translate English to French, cheese to what? What is cheese in French? That's hard, it might be bad. That's 0 shot. So that's this right here. If you actually look at one shot, like translate English to French, see otter to that, and then cheese, right? This is the performance you see. It's way greater. Just with one example of what you want it to do. So we know the models are capable of doing it, right? It's just, we need to elicit that from them. It's kind of hard to get them to know what we want them to do, but they are really smart underneath if we just have to get them to say the right thing and know what we want from them. So yeah, why is this? I mean, the name of the GPT-3 paper was language models are few shot learners, not zero shot learners. That's that's kind of the gist. But what if GPT-3 could be a good zero shot learner? This is pretty much how ChatGPT works today. Boom, look at this. This is called Instruct GPT. This is the exact training pretty much like method they use for ChatGPT today. So I mean, look at this. Like, explain to me that you have a 6-year-old instead of what GPT-3 produced, we have Instruct GPT, which actually gives you a reasonable result, which is pretty much what we're used to today. How they did this. So again, yeah, here's another one. Yeah, look, it actually explains the code. So yeah, how they actually do this is they pretty much just say, okay, so like explain the moon landing a 6-year-old. They give that to an actual person, and they just have a person write a response, and then they just train the model to answer like the person. That's a pretty easy method. So also they paid Kenyan laborers like $2 an hour and like a lot of legal practices to get this training data of like people annotating. Anyways, so this does way better. This is just what we call supervised fine tuning, right? Which is just having people write down the answers. So at first, this is just GPT, right? This is prompting. Remember how we said giving it examples? That's what we're doing there. And then if you fine tune it on actually good answers, it goes to this performance. And what's surprising is, you can have so they train 3 different sizes of models: 1.5 billion, 6 billion, and 175 billion. This is a really big one that they trained, right? But even the really, really big one is lower performing than the 1.5 billion parameter that's fine-tuned or even prompted, right? And it kind of makes sense because if you look back at this, like, I don't care how smart the model is. If it's giving me this, I'm going to rate it really low when I'm looking at it. So yeah, like just for us, this is a scale of us, like humans rated the preference. We care a lot about how it responds to us rather than even if it's super smart and needs prompting. Because we don't care to give it a bunch of examples. How we care to interact with ChatGPT is just tell it what we want, and then it'll give us like exactly what we want, right? So there's this other step, there's this other stuff. I think it's fine to skip over this for now. This is called reinforcement learning from human feedback. This is like you have people rank responses from the model, then you train a reward model off that, and then you use that as a signal to inform generation and to fine-tune the model further. But if you look at that, that goes even better, and that's the entire regimen of Instruct GPT. And that's pretty much how a lot of what's called this like supervised, like this fine-tuning stage after the pre-training is done. Leon.
What's the Likert score?
I think that's literally just like humans. Quality ratings output model 1 to 7. Yeah, I think it's just like humans sat and like gave it a scale rating. I'm pretty sure.
Well, why was there a dip for the 6 billion model for Likert score?
I don't know. Noise. That's interesting. I don't know. Actually, maybe it's a different metric. No, I don't know. Maybe okay. Maybe I don't know that as well. Okay, so take it with a grain of salt. But we find similar. Well, let's see. Quality rating output models 1 to 7 for various models on prompts submitted to Instruct GPT models. Outputs are given higher scores by our labelers than the outputs GPT. Yeah, I don't know. That's really weird. That's strange. Interesting. Anywho, yeah. What? Oh, so yeah, it is. Okay, sorry, I forgot. We have to speed run. Wait, what time? Oh shoot. Okay. Yeah, wow. Yeah, we're trying to speed run. So these are large things about now. Okay, yeah, we're trying to speed run. I totally forgot. Here's the stuff there is today. Transformers are everywhere. Okay. Okay, yeah, forgot speed run. Any questions? Okay, we're good? Okay, good. Okay, wait. That's the first live split. We have to time it. Okay. Next, we're on step 1. Okay, I'm gonna go really fast just so we kind of get a brief overview. To be honest, these other methods I'm gonna talk about don't need you to understand them in depth. It's nice to, but I don't think it's necessary. So yeah.
More about this during advanced track, theory track.
Yes.
In some 6, 7, some weeks like that in the future.
Yeah. So yeah, decoder. Okay. So here are the kind of general steps. Again, I'm gonna go pretty fast through this. We pretty much have to get our like sentence and turn it into tokens, and then turn those tokens into numbers. then we have to, so yeah, that's pretty much like breaking it apart, tokenizing it. And then we have to turn those tokens into numbers. Then we have to add what's called positional embeddings to encode information about how they're positioned in the sentence. Then we pass it through what's called masked multi-head self-attention. Again, I'll tell you why that's a lie. But that pretty much allows information and higher level features to form. Then we have a feed forward to like do some aggregation. You repeat this a bunch where you just keep aggregating higher level features. And eventually you have a linear softmax prediction, and then you can predict the next word in the sequence with those high level features of the sentence sentence so far. So yeah, first step, tokenization. So this is hello ACM AI, how are you doing today? This is actually, if you go to GPT, if you look up, I have that link I thought somewhere, but if you look up tokenization OpenAI, this is actually how it tokenizes your input to ChatGPT. So it has to break those that sentence apart into little smaller blocks. That's the idea of tokenization. And if you actually look, like hello has this ID right here. Space AC is like this ID, right? And there's ways to decide how to break them apart. You could have like a list beforehand of like all the different little parts that you want. One way is also called byte pair encoding. But again, the main idea is just turning the sentence into little smaller chunks that you can break apart, and then those have corresponding IDs. Step 2 is turning those IDs right into actually vectors and have them correspond. And you want those numbers or vectors to actually have semantic meaning. So this is what's called embeddings. What we try to do is have it so the space, the vectors actually can encode semantic meaning. For example, like here, if you have like the vector of man and woman, and you get the difference, and you add that difference to like king, it'll move you to the vector of queen. Like, so like these cool properties in this space is really nice. And it allows the model to actually understand relationships between words. And there's ways to learn that as well, just like skip grammar models and continuous bag of words. But again, these exist. That's all you need to know. Next, we add some information about just how these things are like positioned. Oh, wait, we got time. Got it. Okay, we're on step 2. Wow. Okay. Wow. This is going. Yeah. So next thing, you actually have to not just here. Let's skip the next slide. To be honest, you can't just pretty much just get the word vector that we said, this nice and rich embedding of semantics. You actually have to encode positional information with it. So you add this vector, which is like a sum of waves and stuff. Pretty much, it just allows this new positional embedding to have context of where it is in the sentence. Because if you say like, I mean, think about it. If you put one word, it matters where the word is in the sentence, right? If you say like don't before something or after, it changes the meaning a lot. Sure, that's a rough. Yeah. Okay, this is the big one. Self-attention.
Timer.
Oh, time. I forgot. Yes. It's no way it's been just 16 minutes. Wait, what? Oh, we started at 10. So yeah, okay. Okay, we're not that bad. Yeah, self-attention. Okay. This is like oh, oh my God, my voice is dying. Oh my gosh. Okay, yeah. This is kind of like the main backbone of the transformer, but again, as I'm going to show you later, it's being replaced kind of ish, not really, kind of, sort of. Anyways, I'll explain it though. The main idea is that we have like some word, right? Like let's say it's both, right? And what we do is we turn into that embedding, right? We turn all our tokens into these like vectors and stuff. And then from these vectors, what we're going to do is we're going to pass it through 3 different neural networks, right? A query network, a key network, and a value network. Pretty much, just imagine this has our embedding vector, and we just transform it in 3 different ways, just for some random reason, whatever, right? Then what we do actually is we get all of the tokens which have been passed through and turned into through our key network, and all the tokens which have been passed through our query network, and we actually do a dot product between every single one of them. Or you can think about it as a matrix multiplication. But the main idea is that we're trying to find pretty much like this matrix between the embeddings, which is what's called our attention matrix pretty much. What it's trying to do, this process of passing these tokens through a query and then a key network and then multiplying all and dotting all of them, is we're trying to find the relevance of one word to another word, right, in the sentence. And why are we doing this? Because this is actually the main idea behind the self-attention mechanism is if in the sentence for a word, you can find its relevance to other words in the sentence, you can capture greater meaning of the sentence. So that's kind of like the general intuition for self-attention. So yeah, this process of this dot product passing through query values matrix multiplication is to pretty much form this thing up here. We do a bit of like normalization stuff, whatever. And it pretty much gets down to this. It's just pretty much the same like scaling though. So again, like a word with itself is going to have a high relevance, right? But on, for example, here has a high relevance also to river, because that's what it's on, right? Kind of a little more intuition there. Again, this is like the general intuition of why I think like self-attention works, but also just empirically it works. Like they ran tests with this kind of strategy and it just happens to work really well. Oh, sorry. Yeah, that was a weird slide. Yeah, how relevant they are. So if we actually look at it, this is a better example. We actually can look inside like a fifth layer of this transformer, and we can look at one of these heads, and we can actually see that query key value like multiplication thing. And these are like the strengths, we can visualize it. So like for this head, you can actually see it has a really strong or high correlation value with the animal, because it is actually referring to the animal, which is like kind of cool. You can actually look in these layers and see how these query key value, like once you transform them and you do the multiplication, what the model's actually learning. The model's learning relationships, right? Yeah. So then I'll go to this slide. So then once you have so booked, for example, you have its relationship to all these other words, like hotel has a really high score, A has 0, maybe room has a lot. What you do to capture richer information is you actually create a new vector, right? That is the sum, that's a linear combination sum of those other words weighted by that attention score, right? Yeah, timer. Oh, we're already there. Oh, okay. Okay, we can go ahead. Yeah. So the idea is like, again, there's a lot of processes, and the process overall, I could just say, and it's very algorithmic, but again, the intuition here is that we're trying to turn this, again, this is not just a word, it's a vector with meaning, but we're trying to turn that into a newer vector that captures meaning of the sentence around it, right? And we do that by figuring out its relevance to other words and then turning it into a combination, like a linear combination sum of those other words weighted by the relevance score. So like, look, booked is a lot of itself, like 0.55, but then it's also 0.3% is going to be, or 3% of it, 30% of it is going to be hotel, and then 50% is going to be at. Again, why and how, this is just a mechanism that works. We're just trying to like understand a bit of intuition of why. There's masking, that's a thing. I mean, masking is just another thing that happens here. But if you're like generating, let's say you just have booked and it's looking at, like, let's say this is a sentence you actually have, but when you're training, you're looking at the word booked, right? What's happening is it's relying on the words in the sentence ahead. And that means when you're actually at time of generation, the model might try to like look at words ahead, but they will be nothing. So then it will pretty much just fail. So what you want to do is at training time, you want to mask the future words. So if you're at this word in the sentence, you're not allowed to look at the future words. Or else at inference time, when you're actually generating, it will try to be like, hey, I'm gonna use the future word to predict the future word. And then it's like, wait, I don't have one. And then I'll just fail. Yeah. So yeah. So this kind of idea of this No, I think no, I just did one split. Yeah, we're not there yet. We're not there. Yeah. So yeah. So this is the multi-head part of mast. Yeah, oof, that's a thing. The main idea is, remember that relationship thing I was talking about, right? Where it's had this relationship with, like, this is the orange one I think I was showing, like the animal. The model, you don't want to just learn one kind of relationship between words. You want it to learn a bunch of different kind of relationships that words can have with each other, right? So for this, you're going to have your own, again, these transformations I talked about in the beginning, your query, key, and value matrices that do this transformation before doing all this like attention and stuff. Again, general idea though, you have these sets of for each attention head. So this is called a head, attention head. It pretty much has its own query, key, and value set of matrices. And these matrices go and they do this entire process I said before, where you have this, you first process them through, right? You get your query key value, you get your queries and keys, and you do this kind of like dot product matrix multiplication to get your attention scores. And then you get your values and you use them in the sum here, right? And the idea is that each of these sets of query key values are learning different things, different relationships. So if you look here, right, again, we showed one relationship, but it could be, I mean, like other relationships that it learns. Like, I think the example I gave is verbs to the adverbs, right? So if there's a verb, it have a strong connection to like the adverbs in the sentence. Or if you have like pronouns in it, like, or like even it's saying the subjects they're referring to, right? So each of these different sets of matrices together learn different like word relationship features, right? Yeah. So let's say we have our input, like just two words, like thinking machines, right? And we get our output from one attention head. So this like is now two new vectors, right? Instead of those two, and then now have richer features. And then we have another one, again, this could be like the adverbs to the verbs. This could be subjects to like either articles that reference them. But now we have all of them. What do we pass to the next layer, right? Which one of these features is most important? We don't actually know. So what we'll do is we'll actually concatenate all of them together. But then the problem with that is that's just way too computationally expensive. So what we want to do is we actually get another matrix. This is the feed forward part. And we pretty much get all of those different features that it learned, right? The relationships between adverbs, verbs, and articles and subjects, and whatever else it found helpful. And we concatenate all of them. Then we have this other weight matrix that learns to squish all of them and compress and extract the features you care about, and then get a vector that is the original size that you passed in. So, yeah. Ooh. So, yeah, the idea is you keep repeating this. You had a list of, it's a lot of words right now, but you had a list of tokens, right? Which is your words, and you broke down your sentence. Here, let me just go back a little bit. You had these words, right? And these words turned into these vectors. And then from these vectors, you do this whole process of, you know, having different heads where each head has different relationships and calculated this vector's similarity with these and combined them and aggregated them. End of the day, and then it grabbed all the different features and squashed them down. But at the end of the day, you pretty much just got a new set, the same size as the original vectors, right?
It's like every layer, it becomes a better version of the vector that captures better information.
Exactly. So you're pretty much, yeah, it's pretty much that. So, yeah, this is again a speed run. If you're not getting this, this is yeah, this is a lot. I'm just trying to explain kind of high level intuition, what's happening. But as you repeat this process, these tokens are going to gain richer and richer representations, which means that the attention heads will actually have to encapsulate not just like word relationships of like verbs, adverbs, whatever. You'll have to capture like higher level language relationships, right?
So like at a certain level, once you keep doing it with all these tokens, you're keeping this processing higher and higher and higher. Each token is not going to just represent a word. It actually might represent an entire sentence or idea in that like text you inputted, right? So like a higher level relationship might be like contrastive relationship. So like maybe embeddings at the step, these vectors at this point aren't just representing words, like how we have the semantic meaning, they're representing like entire ideas. And the attention heads are not capturing like just word relationships, but they could be capturing like how like contrastive this idea vector or sentence vector is to each other. Again, we don't know what or how it's really doing it, but again, this is like kind of a little bit of intuition of how it's building a higher level feature of all of these words.
Yes, yeah.
And you just keep stacking this. So that's the stacking part. You do the entire process, and then you have these new set of richer embeddings, and then you just process them again, the exact same process, till you get a really high level feature at the end. And the whole point is once you have a really high level feature, you just pass it through a linear layer that projects it into the dimension of how many words you have, right? And whichever dimension has the highest magnitude, that's the word you want to predict. Yeah, linear, softmax, predict the next word, whichever one has the highest amount. And the idea is that at this point, this rich representation of these words are not just words anymore. These vectors aren't representing just the words. They've been processed so many times and by so many heads and so much stuff that they might capture like the entire meaning of this sentence and things, which can then allow you to predict the next word. Fun fact, GPT-3 has 96 attention heads, and then it does this 96 attention heads like 96 times, which is like insane. That's why it's 175 billion, like billion parameters.
Timer. Wait, is that? Yeah, that's wait.
Section now.
Oh, I did. Okay, wow, I did feed linear softmax. Yeah. Oh, answer question. We're already here.
Sub 30, sub 30.
Wait. Let's see.
Oh,
Oh, wait, oh, okay. Answer. You know what? Okay, we didn't have answer questions. It's sub 30. Okay, I'm pretty proud of that, guys. Okay, that's like pretty impressive. Okay.
Yeah, and same thing here. The idea is that you encode the sentence, and then let's say you want to predict the next word after LLMs are cool, and then you want to predict like the period. You do this whole processing, it happens a bunch, again, it happens n times. And then at the end here, you have this really rich thing that captures the entire sentence. And then, like I said before, you do the linear, you do the softmax, you predict. And what you want the model to learn to predict is this next word here. And you do that for every single word. So again, this word, if you do the linear softmax on this, you want its prediction to be this word. And then this one's prediction to be this word, and this one's prediction to be this word. And that's how you train it. So then actually run like inference time when you're using the model, it's learning to try to predict the next word
as best it can. Yeah, that's the idea. Yeah. I mean, if you want it to, yeah, that's pretty much it. Okay, we can, yeah. Any questions? That was a lot. Didn't fully get it. That's okay. Yeah, Transformers. I'm gonna take a little. That was pretty crazy. That was a lot. Jordan.
is that why for like whenever they say, oh, we have like a sentence, like in every generation, whatever generation, we have a sentence, we have calculated embedding. I remember what they do is because every single sentence we have the end, you have like CLS token, which basically means this is the end of the sentence.
Yeah.
Is that why we use that token at the very end? Because that token is supposed to capture the meaning of the entire sentence.
It doesn't matter for BERT. They have the CLS at the beginning.
Oh.
Again, the main thing is well, it depends because the mass attention, right?
If you have it at the end, then yes, because only the last one can attend to all of them before. But things like BERT, you can just put the CLS here because it doesn't matter. Everyone captures everybody else's embeddings, enriching, like,
I see.
So yeah, BERT has it in the beginning even. So if it's masked, then yeah, it makes sense to have the last one be it. Because you need everything in the sentence to predict the next thing in the sentence.
Oh.
Right. Yeah. Oh, then I'll get to on you first. Then.
So with the self-attention heads, like when you have like subsequent layers after the first one, are they still capturing like the original sequence as well as inputs from the previous self-attention head?
Sorry, say that again?
Like, do you, like, with your self-attention heads, after the first one, do you feed them, like, the output from both the first self-attention head and the original sequence?
Oh, no, you're just passing the next processed embeddings. Yeah, so the original embeddings are completely lost. Though what people realize is very important, which I kind of skipped over. I'm not sure if it's in here anywhere. Yeah, I kind of skipped over it. I'll just go to the first slide. What's very important is this add and norm. The add part is the skip connection. And what the skip connection allows you to do is to carry those features. But the model can choose. It's not all of them. It's not everything. But the model can choose which of the very base level features I want to carry all the way up, right? Because this connection can actually let it, so at the final last prediction, it could actually even somehow have the exact token from the first thing, not processed at all. But it's only if it finds it helpful, right? So these skip connections, I think, are actually really important to the scaling of transformers and stuff, because what it allows it to do is, as it's building higher level features, it allows it to carry the ones it finds important, I think, up with it. That's like, I guess, an idea.
So when you're training the decoder model, you give it like a lot of text, as you said, the text of the internet.
Yeah.
What do you compare that to? Is there like how do you calculate your loss rate?
So yeah, the funny thing is the objective is just to predict the next word. So if I go back to this, it's just with itself, which is really nice. There's no labeling. You don't have to do anything. All you do is you say, okay, this is like a training example. I say, I only have this much of the sentence, right? LLMs are cool, right? And what I want the model to do is take this in, and the label, the output I want to produce is this period. And then here, I'll do another training example. Well, large language models are, and that's one input, and I want the output to be cool, right? So just text in general is the loss and learning objective. It's just to predict the next word. If you have a sentence, you have, let's say the sentence has 10 words, you have 10 different examples you can give it, right? So it's kind of nice in that way. But again, like I said, in the very beginning, you lead to problems where if you just train it on this just very whatever objective, you get stuff that looks like this, right? Which is just the internet. I mean, it makes sense. So what you then want to do is have it so its objective is to predict the next word, but what you want it to do is predict the next word like this, where you give it, you want it so when you say recite the first law of robotics or something, right? It then should predict the next token. The next token should be following your response, right? And that's pretty much, again, the objective. The objective is just predict, next word. Does that make sense? Yeah. Okay. Any other questions? Yeah. Transformer. Oh, please.
Let's say text generation, for example, you have like a sentence, it tokenizes it. Every single word that's put into the transformer is a word predicted after it, like, the moment you put in a token, a word is predicted, or at the end. Like, how does that process go? And if it is one by one, like, isn't there some context lost because you don't have the whole sentence, you're doing it other time.
So, I mean, if you think about it at generation time, let's say I only have this much of the sentence. Technically, you're right. I don't have the rest of the sentence that needs to be generated, but at inference, when I actually want to generate, it doesn't have it. That's the problem. So its objective is to, given the sentence I have so far, try to generate the next word, right? And transformers, the main advantage is, like I said, you can have this example, you can have this example, these three words predict this next word, these two predict the next. You can actually train all of them in parallel at once. That's again, the main advantage over RNNs is that you don't need to process the first word, then the second, the third. You can process this example, then this example, then this example, then this example, and you can do it all at once. And you're not waiting to predict this one. You don't need to wait for this one to process, right? This guy to predict this guy for you to train on this whole thing predicting this thing, right? Does that answer yeah, okay. Another question.
So you said that a Wikipedia is like 3% of the training data, and Reddit is like 15%, if you want more.
Yeah.
Wouldn't that make I would say like a lot of the ideas on Reddit are kind of circulated. A lot of the things are being said over and over again, but Wikipedia kind of has more novel text. Does that get affected? Does it get kind of drowned out? in trade?
Maybe, I think maybe you could say Reddit gives it like conversational skills and then Wikipedia gives it knowledge. I don't know. But just like a lot of text, I think. It's just, yeah, they try to get a diverse amount as well. But sorry, did that kind of answer what is it?
So
Yeah.
my question was like, if Reddit is like 5 times the amount of data, wouldn't it just keep wanting to produce Reddit data, Reddit words, kind of like that?
I mean, Reddit's pretty broad and there's a lot of subreddits where they talk very weirdly about very specific niche stuff. So I mean, yes, but Reddit, I don't think Reddit is that narrow of a thing in language. I think it's pretty.
I guess what I'm saying is like Wikipedia is probably a lot more novel, as you said, more knowledge. But wouldn't you want to like value that over kind of conversational things?
Well, that's the whole point. So the hard part about these models is actually figuring out a way, like a metric to evaluate them. There's like a bunch of different benchmarks, like, but again, like the Likert score or whatever there, really, I mean, you just care about how well it's interacting with you and you'd rate it, right? But there's a bunch of different ways to evaluate it. Like one is question answer. How well can it answer these questions about knowledge? Or one of them is, I think it's called HelloSwag. It's about how well can do like common sense reasoning, which is useful for like also when you like talking like kind of slang a little bit more and like, you know, like using words that aren't like not formal, you know what I mean? So again, maybe Reddit improves that, but doesn't improve its knowledge amount, you know what I mean? So it's just like a trade-off in data set kind of stuff. But if you give it enough, I mean, yeah, like there probably is that concern, but it's again like insane amount of text. Like, yeah.
I think the model is big enough that it doesn't really lose the ability to recall information, even if it is a smaller subset of the training data. And recently there was a paper called Sleeper Agents that basically showed that a model can behave one way on like predominantly, and then we can give it a single token that can trigger entirely different behavior. So, yeah, even if it's like predominantly like answering like Reddit, you could probably have some sort of certain prompt that would make it answer from the Wikipedia data set.
It's big brain, yeah. Wait, okay. Oh, that was, yeah, we already stopped it. Okay, 31, that's good. That's good. What are we at? Okay, wow, we have I can do the rest of that. To be honest, that was like half the slide, so I think we're good. I mean, yeah, it's a lot of setup. Yeah, okay. We're here. You guys understand transformers. That's light work, so easy, right? We're gonna talk about the actual interesting stuff now. Quantization, right? So again, if you want to do the math real fast, GPT-3 is 175 billion parameters. Let's say each one is like a float 32. That's like 4 bytes. If we extrapolate that, that is 700 gigabytes of memory. Like you need it in RAM memory, not like your laptop. Like your laptop, let's say I have a terabyte here. That's not my drive. I need it in the memory. You know, the thing you pay like whatever, I don't know, like $200 more for like 8 gigabytes more. You need 700 gigabytes to run these models.
In the GPU.
In the GPU. Like, yeah. Like, okay, yeah. Let's just like do some math real quick here. So you got an A6000. I think a lot of servers usually have that. An A6000, one of them has 48 gigabytes. And it costs $5,000. If you want a higher end one, like an H100, these are like more expensive end, they're like 30,000 per or 20,000. If you want an A100, I think they're cheaper. But TLDR here, like if you want to get like an A6000, just 48, we do the math, 700 gigabytes divided by 48, that's 14 of these, 14 times, that someone do the math, that's a lot of money, okay? Just to run the model. Like you're using ChatGPT for free, but like actually running it on a server, you'd have to pay that much just to get a GPU, like enough GPUs with RAM to run it. So quantization, wouldn't it be nice if we could compress our model down and make it smaller so it didn't take up so much and I could save my money and eat food tonight? Answer is yes. So here's the idea, crazy, okay? We have our model. Our model has layers. Our layers have weights. Those weights are floats, right? So like,
CS33.
what happens if we make these floats smaller? Crazy idea. Again, like it seems simple, okay, just make them smaller, but what you're doing is you're compressing the range of numbers by a decent amount. I mean, look at this. This is 2 to the negative 149, which is probably like, I don't know, what is that? Like 0.50 zeros and a 1, right? Up to like that, which is 10, like 38 zeros, right? And if you go down to float 16, you go up to like 65,000. And then you go down to like divide by 3, so like 7, 8 zeros, right? Like 0.001 versus 0.0 50 more times than a 1. So like you are reducing precision by a lot. It seems like just half it, but again, there's a reason why researchers or whatever don't just like willy-nilly half it. But
Precision and so range, like that's range. Precision is also like, if you want to move from one number to the next number that's possibly represented, that gap becomes bigger. So like if you have like 0.10001, 0.1002, that may be representable with float 32, but not with float 16. Like it's quantum, like each jump is bigger.
yeah, because this is an exponent. So this is actually the range, but this is actually like fraction precision. So that's what Jordan's talking about. That's some CS right there. Yeah, anyways, I don't care about that. That's fine. So yeah, NVIDIA tried this. That's their graph. They did it. It diverges for some models. Some models it's okay, just doing this has a performance hit, but some models they just completely diverge and they're like, oh shoot, it's not even possible. How do we do this? The solution is mixed precision. So if you actually look at the numbers stored in the computer when doing training and all of this, you have activations, you have activation gradients, you have weights, you have weight gradients, right? So these are the weights of the model. These are how the weights of the model change, and these are like actually the activations and aggregation and summing. And this is the gradient of those like kind of summing and sum at those neurons. And what they realized is that the main problem was actually in these gradients, in that the gradients were super duper small, right? This 10 to the negative, what was it, 50 there? Like what was the range? It went only to 10 to the negative 24, 2 negative 24, right? And this ends like right here, right? And then they realized the distribution of the activations, they were so small, they just clipped to 0, right? This range, this is an exponent negative. So this is like really small. This is really small. This is 0 right here, right? So this is like, again, this is like 1 here, and then this is like 0.000. So again, the gradients are actually really small, they realize, compared to the actual weights of the model and the activations. So
Gradient vanishing,
yeah. But the main thing is that it just didn't have enough precision to actually represent that really small number. So it just went to 0, and then when it went to 0, it just died and exploded, and all this bad stuff happens. So what they realized is, wait, if this is the range of our floats, and this is the range of that our activation gradients are in, what happens if we just slid it over? And this is what they did. So scaling. So what they pretty much did is they just scale it. They pretty much just scale it. You can choose this empirically, right, through statistics or some other methods and things, but you pretty much want it so like the maximum value hits here. That's how they scale it. They scale it so the maximum absolute gradient value is below this. So pretty much grab the max value and then make it so that becomes the top of the representable range. So this is kind of how NVIDIA does it. They call it their mixed precision training. You pretty much have your like a copy, like you have your float 32 weights, but what you do is you make a copy of them on float 16. You do the 4 pass, right? That's way cheaper and way faster. But then when you want to do the loss, you want to have again that granularity and detail in the gradient. So you actually make that float 32. You scale that, right? The scaling is for shifting them over. And then once you scale them, when you actually back propagate those to the float 16 weights or gradients, since they're scaled, it can still be float 16. So again, the backprop cheap, but it's now shifted over into representable range. and then you make a copy in 32, and then you do some clipping, whatever, then you apply that to the master weights again, right? So you still need that float 32 like stuff on the side for gradients and just have copies of to keep the precision of aggregation. But you can actually use float 16 for forward pass and some of the gradient calculations as long as you scale it. And since you scale the loss, when you back propagate it, it'll shift over the actual gradients. Yeah, and this just leads to there's dynamic scaling like you can, as the model's training, you can figure out how the activations are shifting and move them instead of just a constant loss scaling. That's just another thing. But yeah, how good is this? So this is the baseline that is in float 32, and this is where they did mixed precision. So if you look baseline, mixed precision, I think it even looks like it does a little like no performance hit, maybe even better. Again, right here, this is the baseline, right? This is float 32. And if you mix precision with this loss scaling, it's pretty much the same. Again, it's looking better, which is interesting. But if you don't do this loss scaling, if you don't do it so that the gradients are pushed up into a range that's representable, that's the divergence. The model just won't train because again, it has zero gradient. Like it is so small precision that it is literally just cut off. But again, they realize it's not using the upper half of the distribution, so you can just shift them over and use that representable range. Yeah. Any questions? Mixed precision training? Yeah.
So it's after quantization that like there's the scaling issue. So then you scale the gradient so that they cover the whole thing.
Yeah. So when let's say you just wanted to completely just go from float 32 for all the weights, the gradients acted, like everything in the network, everything in the training process, you just want to go to float 16. The problem with that is that some models, not all of them, again, will have this problem. Again, that one did okay. See, that's 60%, we're fine, right? But some of them have this problem with diverging because the gradients get so small that they just go to 0, whereas float 32, they'd be able to be represented, right? So we need to, what we realized is that, hey, they're not using actually the upper half of the representable float 16 range because they're so small. Just shift them up, scale them up, right? So when we actually so then they can be used, right? Because all the values are like 0.0000 all the way down here, and then they go out of range. Why not just push them up into a representable range that we can use, which is over here, right? Any other question? Oh, yeah.
So how much faster does this make it?
I think they said like up to 6, maybe. I forgot. I think they said somewhere.
Like 6 times?
6 times. Here, I can look. Let's see. This is if you guys want to look at this. Loss scaling. Automatic. Oh, here, yeah. 3 times 2x. Video, send them out, yeah. So like, decent speed up, yeah.
When they say speed up, is that for inference or is that for training?
I think it's for everything.
Okay, got it.
Because yeah, the training procedure here, like this forward pass and the backwards pass, you're using just less. Like you can do, yeah, it's just easier throughput. Especially memory bottlenecks. Okay, can we go further? What about like an integer? Can we go down to an integer? Not even like like 32-bit. You can go down to like an 8-bit integer because look at this. Look at this GIF right here. Look, it's 30x throughput. That's an int 4 actually. So sorry, not even an 8. Can we like int 4? And look how fast it is. Like if we could compress our model to an integer 4 versus a float like 16 even. Again, this 16 is the mixed precision. It will be what like 4 times more throughput. Like that seems just like so much better. But if you stop and think about it, int 4 like 4 bits, like 2 to the 4, that is 16 values it could take, right? And you're like, there's no way. I'm telling you, there is a way, which is amazing. So yeah, there's a lot of quantization methods out there. One of them is called LLM int 8. And this does it just basic, just model straight conversion of the weights at load time. And what they kind of exploit is the fact that large language models, the query key value matrices, those things, what they actually do at a certain size is they take on like they have it. So pretty much one of the actual yeah, like one of the actual like columns or layers, or I don't know what dimension we're on, will have like a way larger magnitude than the rest. So if you try to quantize this and do that whole max shift thing, you're gonna have outliers. But what they realize is a lot of large language models will like definitely have at least one or a couple of outliers that they'll know of. So what you can actually do is just remove these outliers, quantize and compress those, because they're all in the same exact range. And then these rest of these numbers you can compress, right? Because if you try compressing this overall, it actually is kind of bad, right? So this is one method I found. It's called LLM int8. I think they have a paper down here and stuff. But yeah, emergence is not sudden. Outliers grow very quickly once this like shift occurs. I think it's around like even 115 million parameter models, then they start to see this like thing where they just have a bunch of like outliers and everything else is like really suppressed. And their intuition is that it's trying to extract like one single feature from the text or something. I don't know. But this is a quantization method that works. Yeah. Yeah. Questions. Okay. Yeah, this is the math. Again, I think it's like, if you look at it, like, again, these are really hard magnitude. So then you want to take those out and then do like a higher bit compression or decomposition on them. And then for the actual ones that are lower magnitude and kind of just there, you can do a smaller compression, like 8-bit compression or 8-bit quantization. Yeah. Okay, so what we just talked about is there's two different main methods of like this kind of int8 quantization or other quantization methods, or even int4 for that matter. The one we just talked about, that LLM int8, is post-training quantization, where you just have the weights and you just do something to them. But there's also quantization aware training, which is kind of what mixed precision is. But first, I'm going to talk about just a little bit more about this kind of post-training quantization, right? So the idea is that what we just showed was pure just grabbing the model weights, looking at them and changing them. But what post-training quantization, this is, again, that technically could be, but this is a little bit more advanced than that method of just looking at the weights. What we can actually do is we can have a pre-trained model and we can get a bunch of calibration data. So we get a bunch of like, let's say it's like a bunch of text or a bunch of images and pass it through, and we can see how the model activates and how it changes and stuff. And we can actually get that distribution of activations, and then we can find scaling factors for each of the layers in the model, right? Based off the data we're going to see, right? Because if you just look at the weights, that might not be enough to understand how you should scale and quantize and what range you should use for the weights. But if you actually pass data through, you can see how these things activate, like what the normal range of these like activations will be. And then you can accordingly shift your range of representable values to be like that. Yeah, that's how post-training quantization works. There's popular methods. You see like GPQ, GGML. This is a pretty popular one. This is used in the Llama CPP repo. There's like LoRA, we'll talk about a little bit. But if you actually look like on Hugging Face and you just look like Hugging Face GML, like you'll see just a bunch of these models, right? And if you see this like GGML, right, this is the type of quantization format that they kind of do. There's a lot of them. I think I even have a little graph at the end here. Yeah, there's a lot. GGML is one of them, using Llama CP. GPQ is another one. If you look at Hugging Face, though, they also have like bits and bytes, which is this is a like an int4 format. This is another kind of quantization. There's a lot. Okay, so I'm just giving like a little survey of the ones that exist, but yeah, a lot of different ways to quantize stuff. So yeah, this post-training quantization, again, I think I kind of already explained, but like if you have like your layer, you pass it a bunch of images, you look how it activates, you see the numbers it produces, and you get the naive way, you can skip the maximum. and then you can get a scaling factor from that.
I'll just go to the next one.
And then you can use that to divide and scale your original things into integers, right? So these are the integer representations, right? And then these are the floats, and then you realize, how do I get from floats to ints? I just have this factor, and the factor is determined by the largest guy. Again, that like n range, right? So like if you have these numbers, you find, hey, the max value I have is 5.4. Okay, then I have this range from negative 127 to 127, right? Because that's 2 to the 7, right? 2 to the 7, negative 2 to the 7. And then you can just divide 127 by that largest value. And then if you want to now get from these guys to map them to a range from 127, negative 127 to 127, you just multiply it by 5.4 or divide by, yeah. Oh, no, sorry. Divide 127 by 5.4 and get 23.5. So I multiply 1.2 by 23.5, I get 28. And then now I can just store these as integer 8 representations. And then when I want to do the calculations, I just scale them back and I just divide and I get my actual weights.
That's like a naive just way of doing it. That's how, again, there's a lot of other ways, but again, this post-training quantization, you pretty much just do this kind of integer representation. You can do some better stuff where it's not just like the absolute range you account for example, like here,
Like negative 127 will never get used because it's not a negative 5.4. So you can actually shift the range and stretch it.
And this is called 0-point quantization. Yeah, more scaling stuff. Again,
The main thing is that you have this representable range, and then you have your actual range of values and that the weights will take on. So you want to stretch and move over the weights so they fit in the range of representable values your format can hold,
right? In this case, an 8 can only hold
negative 127 to 127. So it's a pretty tight range. But if you do this per layer and you actually do
post-training quantization where you have calibration data and you're aware of how it's activating, it actually doesn't do too bad. Can we do better though? So this is quantization aware training, right? So what we do is we do this cool conversion process, but again, it's noisy, there's lossy, there's information, like it's not great. So what, like very brief breakdown, you pretty much, you do the whole thing, you do the quantization, but then you just have it so the model trains for just like 10% more, just a little bit more with the quantized weights. And what this allows for it to do is when you quantize, you probably lost some information and the calculations weren't exactly correct. So it allows the model to learn how to do well with these worse weights. And again, if you train it just with the worse weights originally, I'm not sure how well that would work. Again, that's kind of like the mixed precision thing. But here, the idea is that you have it already trained, you quantize it, has a little bit of error, and hopefully training it a little bit more will allow it to actually learn how to correct for that error the quantization introduced.
So yeah, you pretty much like have your actual weights there. But when you're training, you quantize them, and then that's gonna, again, same with activation, and that's pretty much just gonna add error into your model. And then when you do backprop on it, like this, yeah. So you have your actual weights, you quantize it, and then you do forward pass and you backward pass. And it pretty much is having the model learn how to account for if and when you are going to quantize it and make it have that error. So again, the post-training quantization, you're just pretty much grabbing the weights and changing them, right? So LLM int H just pretty much looks at it, looks at the weights and just does quantization on them. More advanced methods like post-training quantization, you use calibration data to actually figure out what the range is and do more like analysis. And then if you want to go further, you can do quantization aware training where you actually then fine-tune the model a little bit more so it learns how to account for that error introduced.
So making the model like more invariant to if you were to have small shifts in the values of the weights, because that's what happens when you do quantization.
Yeah, it learns how to account for the quantization error.
Yeah.
Let me just see. Yeah. Okay, yeah. Any questions? Any questions? Quantization. There's a lot.
like I said, here's the diagram. Like, there's a lot of different methods out there. A lot of open source stuff. People are using different ones. Like GGML is like really good for CPU, but if you want GPU, you probably want to do an NF4 or a GPQ, I think. Yeah, there are different quantizations and how they like load from memory and all these different things, but a lot of methods, just like a brief survey, little different ones that I've found. Yeah.
So does scaling it not mess with like inference because you're like changing the values?
You scale it, sorry, you scale it and then downscale it, if I didn't make that clear. So they're stored in this like scaled format, but then at inference, you just you do the math to divide all them down and get the representation, if that makes sense.
Oh,
So the storage of the model's smaller. And again, you're only decompress, it's like decompressing, you think about it. They're compressed in 8, but you decompress them to do the calculation, you divide all of them, and now they're floats technically, but you're only doing that per layer. So the memory isn't going to explode, right? If you decompress all of them into float, then yeah, the entire model file will be a lot, but it's this as you go layer, you're just like decompressing, like bring it to float, doing the calculations, then whatever. But the whole entire model is stored as in 8 format, and as you're running, you have to divide all of them by their scaling factors that are stored on the side. So yeah.
Has anyone tried like training like a model with like even more precision and then quantizing it like down?
I don't.
Like like flow 64 or something to see like if that has like any abilities or.
I don't know if people have done higher precision. I think people I don't think people found really any benefit from higher precision.
Yeah.
So like even if you quantize it, it's just truncating the float 32. So I don't think there'd be a difference. That's my guess. Don't quote me on that.
might also take a long time to train because you get caps on it.
Yeah.
Yeah, again, like this thing here, like it depends. So this is these are the different I don't even call them architectures, I guess, of the GPUs or like whatever the instruction sets, or I don't know. But like at first they didn't even have like int4 optimization and like ability. If you did int4 it'd be faster, but then as we got better ones with NVIDIA, you can actually do these different formats and it process faster. Again, if you did this on a CPU and your CPU didn't have int4 operation, then it's not going to do anything, right? That's why like GGML has to be so the CPU can like actually do that. And same thing here. Like it doesn't matter if we do this compression if processing it for takes as long as processing it float 32. We're assuming that the architecture has limitations that make it so it's way faster when we do it for processing and that math. And then once we do that math, we do the scaling. Yeah. Makes sense. Yeah, everyone, we're good. We're good. Yeah. Woo. Okay. That's pretty. Yeah, that's a lot. There's a lot of things. So, yeah. Tips you do per layer. Residual connections you want to do separately. Fine tune for about 10%. Maybe sensitive layers, skip them. Don't quantize them. Yeah, and then you have a good recipe for some nice quantization, and you can run these models like on your laptop. I don't think I have. Wow, okay, I didn't put numbers, but like int4 compression, int4 quantization, I can run like a 13 billion llama like on my laptop in 8 GB memory. So 13 billion times 4, that's what 52 gigabytes, right? That does not fit in my memory, but I can run that 13 billion model on my laptop in like, I think like 8 gigabytes, which is pretty impressive. And again, the performance hit, because we do all this stuff, I don't have another graph for that, but the performance hit is like 95%. Like it's 95% of what it was. So like 5% error off, which is not that bad. You think it'd be way more. It really isn't. Again, even in 4, but again, the idea is like we do it per layer and we do that shift. If we did it overall, we just compressed all, like we just like truncated them all down to int4, I don't think it would work at all. I think it just like collapse. But again, because of these smart techniques and different ways we're doing it, it actually allows us to get only a 5% hit when we've literally reduced it by like 8 times, which is pretty crazy. Yeah. Okay. Time is it? Okay, we got time. I'm gonna take a little
break for a minute. Actually, is there water on this floor?
Yeah.
Okay, I'm gonna get water. We're gonna take a little break. We're gonna take a little break, guys.
Jordan, take
Are you pause it? You pause it?
Yeah, that's good.
Woo! Okay, we're here, guys. We're here. We're back. We're live. Okay. Motivation. This is called LoRA. So we did quantization. That lets you compress your model and run it on your laptop. Great. What happens if you want to actually like fine tune or train your model, right? Again, that whole thing can improve it. But you're still like, let's say GPT-3, you're still moving like 175 billion parameters, right? So some motivation before LoRA, it's called adapters. People just said, okay, what we'll do is we'll freeze all these weights, freeze them. Don't allow them to change, have them be static. Like this is the GPT-3 model staying here. But what we'll introduce is these feed forward layers that these weights can change if you learn. And what this will kind of do is just like a little like push and like modify the actual model, right? So the idea is, I have the graph. Yeah. So if you actually look, GPT-3, if we try, like, let's say we had GPT-3 and it's like generating text, it's great, whatever. We want to fine tune it for like essay generation or like, I don't know, a chatbot for your website. You'd have to move all of these trainable parameters, which is a lot and takes a lot of time and compute, right? But this idea of adapters is we just pretty much have, we freeze everything. We don't let it train or actually update them. We don't need to store gradients. We don't need to store anything for these layers. All we do is we introduce new layers, right? That can then learn to kind of shift around and modify the model, right? And that, like, we can only introduce, let's say, 40 million parameters, right? And we still get pretty good performance and like even better accuracy, right? And I mean, it kind of makes sense. If you want to train like a large language model to write essays versus just general stuff, you don't really need to move all the parameters of like how to write language. You just need to modify it slightly, just a little bit to generate in the direction you kind of want. But the downside of adapters in this way of introducing them where you're pretty much like adding a new layer that will be trained in your model is that it takes longer for inference, right? You have to wait to do this. You have to wait for this layer to process, then this layer to process, right? So you're adding inference time. It's like 30% more. But yeah, it's still way better for compute and training. So LoRA, what it actually stands for is low rank adaptation of large language models. Yeah, it's low rank adaptation. So the idea is we have this matrix. Okay, I'll go with this first. We can get this vector and this vector or matrix, and we can do that. What's called the outer product and create this matrix here. So what happens if we could take our weight matrices and decompose it into two other matrices that kind of preserve as much information as possible, right? That's the idea. I mean, if you think about it, like let's say this is a 100 by 100 matrix. How many values? That's 10,000 values, right? But if we decompose it into like a 100 by like 2 and a 2 by 100, that's what, 400 values, right? 400 values compared to 10,000 values is like orders of magnitude better, right? So that's kind of the general idea about behind LoRA. So if you actually did this with the original weights, though, you'd just be losing an insane amount of information, right? But again, remember, what we're trying to do is fine tune or change them. So what we actually want to do instead is we can store a separate weight matrix that is like a copy of our original, but it's a difference, right? So this is the base model, this is GPT, right? And this difference will be us fine tuning it or training it for essays or something, right? Or for our chatbot for a website. So we don't actually need to, you're not modifying the original weights. We're storing a difference that we should modify the original weights to get our like fine-tuned model, if that makes sense, right? Because from this model, we're gonna change it, fine-tune it, and the weights will be different, right? But what you can just do instead is just store that difference as a separate file. And you're like, okay, wait, why does this help? You're just pretty much copying it. That's the same size. Even if you do all the math and stuff on this difference file, it's still the same number of parameters. But again, remember that thing of decomposing. We actually have it. So this difference is this decomposed thing over here.
So we have it so the original weights are just still there. We still have the original copy, but when we're fine tuning it, we have it so the differences are stored in this like decomposed lower rank kind of format. Yeah, that's the general gist. And go have a look. I'm just gonna go to Jordan real fast. Yeah, so Jordan is a good example. I still Jordan's slide. So let's say you have like a diffusion model that generates images, right? It's like, okay, I want to now generate like cats, right? Okay, so I have the base stable diffusion model. It's 5 GB, by the way. And then I want to have it fine tune it on a bunch of images of cats, so it generates cats now. I do that. I now have a cat 5 GB model. Now, if you want to generate cats, I have to send you a 5 GB file of like, so it can generate cats, right? But let's say now I want to generate portraits or iPhone looking photos. Then I have to train another 5 GB model and send it to you. What LoRA allows for is everyone here just has their stable diffusion base 5 GB model. And what I do is I have the LoRA be this decomposed smaller amount of weights difference file. And I can just send you this difference file of how to modify the original weights to get to the fine-tuned version. And that LoRA file is only like 30 megabytes, right? And as long as everyone has the original model weights, I can give them a really small file that's the difference. Again, if I just gave you the actual difference, it would be the same size, right? It wouldn't help. You'd just be sending another 5 GB file to say subtract all these values. But if we decompose those weights into smaller ones, again, 10,000 versus like 400, as I said, you can get them way, way smaller. So if we actually look at it, so we had GPT-3, 175 billion parameters. They reduced it by the difference file. They made it so the trainable parameters is 10,000 times less, right? And then actually see it's 10,000 times less, just like adapters did, right? But the difference is you're not adding to inference time, right? And it's on par or even better performance than just fine-tuning the entire 175 billion parameters of the model. So yeah, that's pretty cool. We can somehow store not fine-tune the entire model. We fine-tune the like differences, but the differences don't need to be the entire super accurate. They could be this low rank decomposition of the matrices. Why does this work? Like, you know what I mean? It feels like if you're showing a difference, like the error should still be there. Oh, here's some more results. The rank they have, like let's say it's 100 by 100, and they do 100 by 2 and 2 by 100. That 2 right there is the rank, right? So if I did like 100 by 4 and a 4 by 100, the rank there would be 4 because there's 4 dimensions it can represent there. That's a little linear algebra there for you. But what they realize is, let's say they have only 18 million parameters for this difference file for GPT, right? GPT is actually, 175 billion parameters. But let's say they say just 18 million for this difference, right? This low rank decomposition difference file. What they showed actually is that you don't need a really high rank. Like, let's say it's 100 by 100. You don't need a rank of, 100 by 50 and a 50 by 100. You don't even need a rank of like 100 by like 5. Like, you need like 4. Like 4 is probably optimal. Even 2 works, which is like very, very impressive. Again, these are the query key value and I think P4 layers. And what they realize is it's instead of pulling all of them into just like maybe having 100 by 8 and 8 by 100 just for the query, they realize it's best if you go even 2, but you spread it out across all the weight matrices that we have. You do query key value, and even if you have 2, a rank of decomposition of the matrix of 2, it's still very performant. Again, if you look at this, for example, this is a rank decomposition of 1. You see like 1, right? But imagine this was 1 more, right? That'd be 2. That's what that R means in these graphs. Yeah, pretty surprising that you could have such a low rank, and it's kind of like that feels wrong kind of at first, but then the more you kind of think about it, like I said before, the entire space of generating images or text is like what is stored, again, this is like intuition, stored in these like 175 billion parameters, right? You don't need to change all of the 175 billion parameters to, instead of generating text in general, to generate essays or generate pictures of things to generate pictures of cats. You know what I mean? It's not that complicated in the image space. To be honest, it's a very like simple direction or dimension change, right? And that's why we can decompose the difference in such a low dimension, is because the difference in, like, think about all images, just noise you can generate. That's like a lot of just different things you could generate, right? The model, the 5 GB model already knows how to generate images. You don't need another 5 GB model to just tell it to generate different images. You can actually have a really small file that just tells you how to generate it in a certain different way, right? And the thing is, it actually trains faster and better because you're not forcing the entire like image space to come along with you. That's like a little bit of what they kind of alluded to in the paper. Subspace similarity, again, if you do a rank of 8 or even 64, they show that pretty much after the first like 8 dimensions, eight top like singular value decomposition, 8 of the most important dimensions, it's just noise. The rest of the dimensions really don't help when you're doing fine-tuning and differences. It does help when you're like actually generating images, but again, this difference fine-tuning training, you really don't need that much information to store the difference of fine-tuning, right? So that means when you're fine-tuning, you shouldn't be fine-tuning the entire model and all the weights. You should just be fine-tuning this like little side difference file. And that's really what trains faster, better, and allows you to give this file, this LoRA checkpoint, people call it, to other people. And I can give you, hey, you have the stable diffusion model. Here's one to generate cats. Here's one to generate portraits. Here's one to generate anime figures. Like whatever you want, you can just have that fine-tuned version of the model in like this little file you store. And that's because the subspaces, if you even if you make that file larger and larger and larger, it's representing the same subspace of images and text. It's not really helpful to make it larger. It actually might make it slower to train and more bulky. There's no reason to, which is kind of cool. They back it up with math and stuff. And then, they compared, what was cool is that they compared the delta file to the actual original weights. So the change in weights compared to the original weights. And they were like, okay, is the change in weights just completely random directions that the normal weights don't like kind of point in? If that kind of makes sense through, again, they had some math formula. But what they realized is that it actually had a strong correlation with, it had a stronger correlation than random weights. The delta had a stronger correlation with the original weights than like some random weights, which showed that the delta weights actually were pointed in the same direction as the original weights of like image generation or text generation. It just happened that one of the dimensions is amplified way more than the other. So second, instead of repeating the top singular directions, the delta weight file only amplifies the directions that are not emphasized in the original weight file. So it kind of makes sense. Like if you have here image generation, it can generate cats. You're not trying to teach it, like it can generate cats, it's just not generally gonna do that or good at that. It's not like you're just gonna completely generate like random noise images. You just want it to amplify that cat generation or this certain kind of trait it has. And that's what the fine tuning does. The model has that kind of knowledge in it. You just need to like, push it in that direction. That's what the fine tuning process is. When you have ChatGPT, you're not fine tuning it to train it to give it more knowledge. It has the knowledge of how to have a conversation or has the knowledge how to generate essays. You're just fine tuning it so it can push it more in that direction. And this is kind of cool. LoRA, this breakdown of a difference file and stuff, kind of shows how and why this works, and also like backing it up with like cool math stuff and like subspaces and like value decomposition, which is like super sick. Yeah. Any questions? That's LoRA. It's pretty cool. Cool. You can fine tune way faster, send little files to your friends as checkpoints, little modifications to the model.
For the orange part over there, practically it's just implemented by 2 feed-forward layers, one like reducing the with input size D, output size I, one with input R, output D.
Implementation wise, it does an outer product. of the two things, and if it does an outer product of the weights, and then it forms the original matrix, and then adds that difference to the original weights or subtracts it, and then
Let's say you have like a matrix W, right? So you're like tossing it like WX.
Yeah.
And you did the outer product and you split W into like A and B.
Mhm.
So you have like A and B X. Isn't it the same as just doing like BX and then A times that? So that's just 2 feet forwards, right?
maybe, I don't know.
It is just
That-
2 people forward, basically. But like, you're not really trying to pass like the weights through the feed forward. You're using these two feed forwards to approximate the weight.
To approximate 1
Yeah.
feet forward to combine both of them. those
Exactly,
moments.
yeah.
I mean, it doesn't have the bias.
Also, how does this work for like CNNs? They just do on like the channel dimension
It's-
for LoRa.
I think they also said something very, hold on, wait. Did they talk about skip connections here? I don't know. I don't know. Did they, wait, sorry, what are you saying? Wait, what?
Like, how would you do this for CNNs? Because CNNs aren't just simple feed forward networks. Like, do they do it on channel dimension then?
Oh, all I know is this on transformers and
Okay.
yeah. I haven't seen it on CNNs yet. So maybe it might not exist for that reason because it's hard to implement that way or nobody knows.
Huh.
I've mostly seen it for stable diffusion stuff and just like
Okay.
people trying to train like llama, right?
Yeah.
So again, like I said earlier, like llama 13 billion, I can compress it and get it on my computer, but like it still doesn't like to say bad things or generate text that I want it to or something. So if I want to fine tune it or train it, what I can actually do is just I have the llama file on my computer. I can just go look up online and find someone's checkpoint of a LoRa, which is just like a couple megabytes, and now I can have it generate like essays or any text that I want, or be a fun chatbot or anything, right? Same thing with this stable diffusion. You can have it just generate any kind of style you want. I think these are LoRa checkpoints. They're just like generate different versions, and they're just like little files. As long as you have this original 5 gigabyte checkpoint, you're pretty much good. The time looking like okay. Yeah, there's also Q LoRa. Just it's quantized LoRa. You quantize while you're doing this LoRa training, and does even better. It adds inference time because when you're training, you're compressing, decompressing actually, so it doesn't speed it up, but it makes it so your memory usage is less. It's another thing. So it combines both of what we just talked about, quantization and LoRa. Thought I'd add that. Also, yeah, there's like also floating like 4 bits. So we did 4-bit integers, but they also have floating 4-bit, which is kind of crazy to think about the range. Again, it's 16 values. But yeah, that exists. That's what NF4 is. Yeah. Okay. Any questions before we move on to the last thing here? No? Okay, we're gonna hit it. This is the stuff. This is the stuff. Okay, remember attention? This drives me crazy. Okay. Okay. This is an AI theory here. Okay, put your tinfoil hats on. Attention, all this stuff. Everyone's talking about it. It's like this is the big thing. Remember, I showed the whole intuition, like the relevance to stuff and like aggregating and whatever. A lot of papers come out, they're like that's BS. Like yeah, he did. No, don't remind me. I remind myself when I looked at that, but it's okay. Anyways, recap. This is like a vision transformer. Instead of having like tokens of words and stuff, you can actually get an image, get patches, and convert those patches, like treat them as tokens, and you can pretty much be state of the art. Like transformers are just really powerful. This is just like just one architecture called vision transformers. Yeah, again, instead of words in a sequence, you have patches of an image, and you use that to classify the image as whatever. That's a thing that exists, and it works really well, which is kind of crazy. So this paper came out called Metaformer is actually what you need for vision, which is a little like, what is a metaformer? They just made up the term, that's the point. But this is the general architecture of a transformer, right? You do this kind of attention thing, and then you do the channel MLP, which is the, you remember how you get all those outputs of the attention heads, you concatenated, compressed, and did all that? That's what this part is, right? The attention is the combining of the tokens, right? But what they realized is you can abstract this idea. The first step is just a token mixer. You're getting all of the tokens or words in your sentence. And again, we did self-attention to mix them,
right? Where we grabbed, like, we figured out, okay, this guy has this much relevance, these guys, so he's gonna be a linear combination and aggregate them to a higher level, and each one of them is gonna do that. They're like, you don't need this self-attention scheme. You can do it by any means necessary. They did pooling, which is like, this guy become the average. And that's it. They literally just did average. There's no learned weights. There's no nothing of learning which guys to pay attention to, whatever. They do just an algorithm of combining them. And what happens is that they completely remove the self-attention with pooling, and they achieve, where is it? They achieve like equal to, or actually, well, it depends on size and stuff, but they achieve like 92% performance or 97% performance, which is like insane, or even better for smaller sizes, whatever. It's like comparable, which is super weird. You're like, wait, I thought attention was this whole thing. And you're like, okay, but this is maybe just for that vision, vision, we're doing patches and stuff. Maybe this doesn't apply to like text. Maybe text still needs this self-attention mechanism, and that's really important, right? Oh yeah. So real fast metaformer though, 74% accuracy, yada yada. Oh, if you actually what is this? Oh yeah, residual connections also are very important. So again, the self-attention isn't really, but again, like Leon was saying earlier, the actually to carry up the signal, if you remove this self-attention thing, you think, okay, you can remove attention, replace it with this like averaging. But if you remove this, they don't train at all. So these things called skip connections are actually very, 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 very important transformers, more than any other, I think you say. But yeah, replacing self-attention with pooling, and you're like, okay, maybe this just works for like images, because some reason attention isn't as important, self-attention, and like averaging is like kind of more important, right? Let's go to this one. No, these guys replaced the self-attention with a Fourier transform. Instead of averaging, they just did like Fourier signal, whatever, like aggregation. So yeah, it's a lot, but they replaced it with, again, like an algorithm, like no learned weights. It's just grab these guys and combine them by how far away they are from me, right? And you're like, okay, but this is vision? No, this isn't vision. This is actually on text, like language, right? And if you compare this to BERT, what they showed was they got 92 to 97% of the performance, completely getting rid of self-attention. There's no self-attention here. It's gone. That entire thing I explained of all of that is completely gone. They ripped it out. There's not even weights. Again, we have those query key value matrices. Those were learned. The model learns how to change them. But there is no learning. The model learns nothing. It's just like an algorithm where it's like, okay, if you're here, you combine all these guys. If you're here, you combine them like this. And it's just a static algorithm that doesn't learn how to change depending on what input, nothing. And they achieve 92 to 97% of the accuracy of BERT, which is like the original like transformer with self-attention and all that. Which is like, and it trains faster because it's like this is an algorithm, right? It's like, wait, what? I thought self-attention was like this whole big thing and whatever. I don't like, but a lot of papers are coming out and it's like, you don't really need it. So this kind of paper kind of summarizes it. The idea, the abstraction of all this transformers, what they're really powerful, why they're really powerful, is that all they're doing, self-attention was the mechanism, but self-attention, what it did, it just mixed all the tokens in the spatial dimension, right? It grabbed, like, there's a token here, there's some tokens or words over here, and it just aggregated them. It doesn't matter how you aggregate them, you just need to aggregate them in some nice way. And then, once you aggregate them in some nice way, you then do that again in a different way, and those are all in your heads. And then all you need to do is, like I said, remember how you concatenate all of them, and then you need to compress them or combine them in another way. So the scheme is pretty much, you need to mix the tokens spatially, right? And this is through, you can use just a dense layer, or again, we use self-attention. We don't need to. And then you just need to mix them through the channels and feature dimension. And that's it. That's the scheme. If you actually look at all these, that's all they're doing, right? You're doing this kind of just mixing spatially, right? And then this channel LP, this is concatenating, grabbing all those features. It's mixing all the features together. So you just need to mix all the actual things spatially, the tokens together, the patches together. And then once you just get a bunch of features, you need to mix all those features together. And that's it. And you can get rid of the self-attention, get rid of whatever. you can replace it purely with just a dense layer. You don't need this whole complicated thing, like a normal neural net layer, just which looks with like a neural net that looks at all the things and just combines them like a dense layer. And then you just do that along all the features that you aggregated, and you keep repeating, and you should get comparable performance to the original transformers, which is like what? It's kind of just crazy. Yeah, I don't. Yeah, I wonder why it's not as. I don't know. If you guys, if anyone knows or wants to read up on this and come back to me and talk about it as well, I would love to, because I feel like there's something I'm wrong with here, but like the numbers are there. I don't know. Oh yeah, this is just some other stuff. Yeah, that's about the time. Oh, we have a little time. Oh, we'll go a little more. There's some other works. This is just some other stuff. Attention is a lie. But again, the problem with attention also is not just you're like, okay, why do we care to replace attention? Who cares if you use something else? Attention is actually quadratically scaling, right? So when you add another word to the sentence, it needs to form attention with every other word, right? Which means as your sequence length grows, let's say you have a book in there in your context window, right? It's 100,000 words. You have the 100,000th word. It's like, oh my gosh, how many calculations am I have to do? It's quadratic compute and memory, because you need to store the attention scores of all the previous ones. So it's kind of good and nice if we can replace self-attention with something cheaper and less memory intensive and computationally easier. And there are some benchmarks. These are just some benchmarks, but there's cool ways they evaluate the model. So like that vision transformer, they evaluate it to see how well it can figure out if like one dot is like connected to another dot, or image classification. They have like pixels, and they say like, yeah, I don't know what that one is, but they have a bunch of different benchmarks of evaluating these models. Yeah, this is some other stuff. But look, FNet is here. This is how well it does on that Pathfinder thing. It actually does very well. Like again, a Fourier transform. If you look at the actual transformer, it does worse. So somehow it even does better performance. But the reason why is that again, like that quadratic scaling and compute and things like that, it's better out. It's better performance. Kind of rambling at this point. These are cool papers. This is cool stuff. This stuff at the end, to be honest, I'm just looking at right now. This everything here, I saw this a while ago, but all of these, like, I'm kind of ad-libbing because I just found these papers and they look really cool. And it's kind of just saying how like all the things I thought were right were kind of wrong. And you can get, 92% to 97% performance somehow. And then also like there's these cool benchmarks which show like the transformers don't even do that well, and these other ones actually do, and it has the benefit of non-quadratic scaling and stuff. So yeah, that's just like what's happening now, what is out now, what I'm looking at least. But yeah, that's it. Next week, that's it. That's then. That's the lot. Any questions? Yeah. Okay. I think that's a no. Everyone's it's the lecture.
Next week, we have Daniel coming, who is one of the co-authors of Stable Video Diffusion, to talk about the current state of generative video models and what he thinks is next in the field, which is like the new hot thing that people have figured out how to generate images pretty reliably. So people can film the video. Yeah. So what are state space?
Oh, state space. Okay, I can just sit for a little. State space models. It's super cool. It's like so the problem with like transformers is you have that quadratic thing where you need to store the entire attention matrix, right? So when you add one more value, you have to store like a larger amount of scores.
Right.
But what they realize is if you remove the softmax, right, which in the beginning, which scaled them down, it then makes it so the attention scores can be linear, right? And then you can carry them through. So you can pretty much make it like an RNN where you're carrying through your query key value, like your softmax, like your attention scores, and then you just like can append like onto them. So it's making them like an RNN. But at like training, you can still do parallel, but at inference, because you're doing that, it's linear in memory, which is like, what, how are they doing that? And they're doing it through, if you understand, this, again, this is like a lot of math. This is like control theory. It's state space models. If you know, I don't know what it is, but, it's like this math. If anybody understands this math,
Oh,
does anybody understand this math? I don't know what this is. It's like some differential stuff, and it's like control theory. And it's like they realized you can represent models and like their prediction with like control theory of like a signal and predict like the next step or something. And it's like I don't even know. Like look this blog is like crazy, like long. Like look at this. He's like giving you a physics example. This is like about neural networks. And he's saying like, look, this is how like the control, it's like a PID, like it controls how it, right? And then he's like, look, this is the math, and like you can represent it recurrently, and like, yeah, there's a lot of stuff. But the whole point is that it's not quadratic, right? With the attention, you don't have to store all the values. You can actually store linear. So like if you're at the 1,001th word, it's not going to cost any more. It's just going to cost one more instead of you have to compute it with everything, which is like way nicer. But again, there's that trade-off of like compression and stuff. But they're like, it's not that bad. I think it's just an abstraction of what everyone's trying to do, because some people are trying to just do linear transformers where they're not that, but then some people trying to do other stuff. They're like, no, this is all just a structured state space model, and you can just represent it like this. I'm like, okay, I don't know what that is. How much math there is. Like, look at this. What? Yeah.
So am I correct in that it's FNet? You can make with FNet you can make a fully connected, like only fully connected linear layers. Make a model like that outperforms a transformer.
It is outperformance. I think this one is 92 to 97% of performance, but on the long range other benchmarks, it actually does it did do better, which is weird.
Wait, so this is a linear fully connected network. Like it doesn't have anything like convolutions or
No, this is just transformer, and we just replace self-attention with Fourier transform.
Is Fourier linear?
no.
Unless you're doing n log n fast Fourier
Right, you can do FFT.
FFT.
You would have to.
Oh,
No,
wait.
you don't, otherwise the network would be linear.
Wait, this is the crazy thing.
No linearity or activation layer.
I have one last crazy thing, which is why FNet works so well. Again, the other ones didn't work. The averaging didn't work as well for transformers. It's so cool because Fourier moves you into like, it turns like time series into frequency.
Yeah.
It is literally doing the shift from spatial to feature dimensions. So then when you do the mixing, it's mixing the feature dimensions, and then the next like layer, you're now switching back to the spatial dimension and then feature dimension, because like Laplace dimension, right? Like,
So does that mean you have an even number of layers?
I think you should, yeah, probably.
Yeah.
But it's kind of crazy. Like it is doing this transpose, right? That's literally what it's doing in the spatial and feature dimension. And that's what a Fourier does on a signal. Like a Fourier transform on a signal converts the spatial signal of time series to then a frequency. And then you're converting back. If you do math in the frequency, then guess what? You're now convolving and aggregating the actual like normal time series signals, which is like, that was like what they said of why they think it works. And I'm like, what the heck? That's crazy. They don't like,
That employs is called Fourier neural operators.
what is it called?
Fourier neural operators.
Is that what they pretty much like the same?
That was pretty recent, but it's like very similar logic to what you're saying, you know.
Might also help that embeddings, the position embeddings are assigned bus rates. When you decompose them, like,
Yeah. I think to be honest, we didn't have. I mean, without positional, I think you're just like everything is done. Like, yeah. I think that's it. Yeah. It's 1:45. Any other? You just want to talk about anything? I think we're all done. I think it's like a 2-hour lecture, and we're
All
wanting to go home.
All right, see you next week.